When I talk about black holes on this channel, I often say that they are not just objects in space. They are tests of our deepest ideas about gravity, quantum mechanics, and the universe as a whole. Black hole entropy is one of the sharpest of those tests. It forces me to connect gravity, spacetime, thermodynamics, quantum fields, and even the large-scale fate of the universe. So in this monologue, I want to walk carefully through what black hole entropy is, how we discovered it, why it matters for dark energy, dark matter, and cosmic expansion, and what we still do not understand. I start from something familiar: entropy. In ordinary thermodynamics, entropy measures how many microscopic configurations correspond to the same macroscopic state. A box of gas has a certain temperature, pressure, and volume. Those are macroscopic. But at the microscopic level, the gas molecules can be arranged in an enormous number of ways that all give the same temperature and pressure. The higher the number of microscopic arrangements, the higher the entropy. Entropy also has a statistical direction. In an isolated system, entropy tends to increase. That is the second law of thermodynamics. It is not a law about purpose. It is a law about probability. Systems evolve from less probable, more ordered states to more probable, more disordered states. Now, gravity complicates this picture. In everyday thermodynamics, we usually ignore gravity. But on cosmic scales, gravity is dominant, and gravity is attractive. If I take a diffuse cloud of gas in space, the highest entropy state is not an even, uniform spread. Gravity pulls matter together. The cloud fragments, stars form. At first sight, this looks like increasing order. Structures appear, but the entropy of the gravitational field itself increases. Collapsing matter can radiate energy away as light and heat, increasing the entropy of the surrounding radiation. And in general relativity, the deepest gravitational wells are black holes. So a natural question arises: what is the entropy of a black hole? For a long time, the naive answer was 0. A classical black hole in general relativity is extremely simple. If I ignore electric charge and spin for a moment, it is fully described by just one number: its mass. This is often summarized by the phrase, "black holes have no hair." That means many different configurations of matter and radiation can collapse and form the same black hole. From the outside, all that complexity is gone. If I think in thermodynamic terms, a system with only a few macroscopic parameters and no visible internal degrees of freedom looks like a system with 0 entropy. But that leads to trouble with the second law of thermodynamics. Imagine I have a cup of hot tea with some entropy. I drop it into a black hole. Outside the black hole, the tea and its entropy disappear. If the black hole has 0 entropy, the total entropy of the universe, as seen from the outside, has decreased. That would violate the second law. To fix this, Jacob Bekenstein in the early 1970s proposed something bold. He suggested that black holes must have entropy. That entropy should increase when matter falls in. And he argued that the entropy of a black hole should be proportional to the area of its event horizon, not its volume. The event horizon is the surface beyond which nothing can escape, not even light. For a non-rotating, uncharged black hole in general relativity, the Schwarzschild solution tells me the horizon radius is proportional to the mass. Specifically, the Schwarzschild radius is 2gm4c². The horizon area is then proportional to the square of the mass. So if the entropy is proportional to the area, the entropy scales as the square of the mass. That is very different from ordinary matter, where entropy usually scales with volume, which scales with the cube of a linear size. Bekenstein did not know the exact constant of proportionality, but he guessed the form. Then, Stephen Hawking did something that changed our understanding of black holes and spacetime itself. He combined quantum field theory with curved spacetime and asked what happens near the event horizon. In classical general relativity, black holes do not emit anything. They only absorb. But when I consider quantum fields in the curved spacetime of a black hole, the vacuum is not so simple. Hawking showed that black holes must emit thermal radiation, now called Hawking radiation. The spectrum is that of a black body with a temperature inversely proportional to the mass of the black hole. Large black holes are very cold. Small black holes are hotter. Once Hawking derived a temperature, thermodynamics told him the rest. If a black hole has a temperature T and a mass energy E equals mc squared, I can use the first law of thermodynamics, D equals Ts, to compute the entropy S. The result is the Bekenstein-Hawking entropy. It is proportional to the area of the horizon divided by the square of the Planck length. In symbols, S equals kBA, 4LP squared, where kB is Boltzmann's constant, A is the area, and LP is the Planck length. The Planck length is about 10 minus BC meters, so LP squared is tiny. That means even a modest astrophysical black hole has an enormous entropy. For example, a black hole with the mass of our Sun has an entropy around 10 in units of Boltzmann's constant. A supermassive black hole in a galaxy center, say with a mass of 1 billion suns, has an entropy around 10 hum. If I compare that to the entropy of ordinary matter and radiation in a galaxy, the black hole dominates. This leads to a striking conclusion about the large-scale universe. The total entropy of the observable universe today is dominated by the entropy of supermassive black holes at the centers of galaxies and clusters. The entropy in the cosmic microwave background, the relic radiation from the Big Bang, is large but still smaller than the combined entropy of all those black holes. This connects black hole physics to cosmic expansion and the fate of the universe. As structure forms over cosmic time, matter falls into gravitational wells. Some of it ends up in stars. Some of it ends up in diffuse gas. But a significant fraction, especially in massive halos, eventually finds its way into black holes. That process increases the total entropy. If the universe keeps expanding and structure formation slows down because of dark energy, we expect a future in which most ordinary matter is either locked into black holes or dispersed as very low-density radiation. The entropy budget will be dominated by black holes. And if Hawking radiation is correct, in the very far future, those black holes will slowly evaporate, converting their mass into radiation and increasing the entropy of the surrounding universe even further. Now I want to pause and ask what this entropy really counts. In ordinary thermodynamics, I can say, entropy is the logarithm of the number of microscopic states compatible with the macroscopic state. But for a black hole, what are those microscopic states? In classical general relativity, the interior of a black hole is hidden behind the horizon. The equations do not tell me about individual microstates. Yet the formula S equals A, 4LP squared, suggests there are SKB distinct quantum states that all look like the same classical black hole from the outside. This is one of the central puzzles of quantum gravity. Different approaches to quantum gravity have tried to explain black hole entropy by counting microstates. In some versions of string theory, certain highly symmetric black holes can be modeled as bound states of strings and branes. For those systems, people have been able to count the number of quantum states and show that the logarithm of that number matches the Bekenstein-Hawking entropy formula, including the factor of 1/4. That is a major success for string theory. In loop quantum gravity, another approach, the area of surfaces like horizons becomes quantized in discrete units. Counting the number of ways to build a horizon with a given area out of these quantum area bits can also reproduce the area law with some assumptions about the underlying quantum geometry. These are not yet complete theories of nature, but they show that it is possible, in principle, to interpret black hole entropy as counting microscopic degrees of freedom of spacetime itself. The fact that entropy scales with area, not volume, suggests something profound. The fundamental degrees of freedom of gravity might be organized holographically. In a hologram, a two-dimensional surface encodes a three-dimensional image. In gravity, the idea is that the information content of a region of space is bounded by the area of its boundary, not its volume. This is sometimes called the holographic principle. Black hole entropy is the most concrete example. The maximum entropy inside a region of space of a given size is achieved by collapsing all the matter into a black hole. The resulting entropy is proportional to the area of the horizon around that region. That gives me an upper bound on how much information can be stored in that region. This holographic viewpoint has been made precise in some special cases, like the 8s-CFT correspondence in string theory. There, a gravitational theory in a higher dimensional spacetime with negative cosmological constant is exactly equivalent to a quantum field theory without gravity living on the lower dimensional boundary. Black holes in the bulk correspond to thermal states in the boundary theory. The entropy of the black hole matches the entropy of the boundary field theory. That is a very concrete realization of holography. Our real universe, however, is not anti-de Sitter. It is closer to de Sitter, with a positive cosmological constant due to dark energy. We do not yet have an equally precise holographic dual description for de Sitter space. That is one of the open problems when connecting black hole entropy, dark energy, and cosmic expansion. Now let me bring in dark matter. Dark matter is a form of matter that interacts gravitationally, but not, as far as we know, through electromagnetic radiation. It clumps, forms halos, and drives the formation of galaxies and large-scale structure. When I consider the entropy of the universe, most of the entropy is not in dark matter itself. Dark matter is cold and relatively ordered in phase space compared to, say, photons. But dark matter shapes the gravitational potential wells in which baryonic matter collapses and forms black holes. So dark matter indirectly controls where black holes form, how massive they become, and how they merge. In that sense, dark matter sculpts the entropy landscape of the universe. The largest black holes, with the largest entropy, sit in the centers of the most massive dark matter halos, like galaxy clusters. Dark energy affects black hole entropy in a different way. Dark energy, or a cosmological constant, accelerates the expansion of the universe. In a universe dominated by a positive cosmological constant, there is a cosmic event horizon. Beyond a certain distance, light emitted now will never reach us. That horizon also has an associated temperature and entropy, similar in spirit to black hole horizons. The de Sitter horizon entropy is proportional to the area of that cosmic horizon. For the observed value of dark energy density, the de Sitter horizon entropy is huge, much larger than the combined entropy of all black holes today. If the universe approaches a de Sitter phase in the far future, the maximum entropy accessible to an observer is set by this cosmic horizon entropy. So we have at least two types of horizon entropy to consider: black hole horizon entropy and cosmological horizon entropy. This raises subtle questions about the ultimate fate of the universe. In a dark energy-dominated future, structure formation freezes out. Galaxies that are not gravitationally bound to us recede beyond our horizon. Locally bound structures, like galaxy groups and clusters, remain together. Within those bound regions, black holes continue to grow for a while as they consume stars and gas. Their entropy increases, but because of cosmic acceleration, distant regions become causally disconnected. The second law of thermodynamics applies within each causal patch. The total entropy in our observable patch will be dominated first by supermassive black holes, then, after they evaporate, by the low-energy radiation and particles they leave behind, plus the entropy associated with the cosmological horizon. I want to stress that some parts of this story are very well established and some are not. The Bekenstein-Hawking entropy formula is supported by many independent arguments. Hawking radiation is derived from quantum field theory in curved spacetime, which is a robust semi-classical framework. The idea that black holes have entropy proportional to their area is widely accepted. The role of black holes in the entropy budget of the current universe is also relatively clear, based on estimates of supermassive black hole masses. The existence of dark matter and dark energy is strongly supported by observations of galaxy rotation curves, gravitational lensing, the cosmic microwave background, and the accelerated expansion inferred from supernovae and large-scale structure. However, we do not yet have a complete theory of quantum gravity. We do not know exactly what the microscopic degrees of freedom underlying black hole entropy are in our universe. We do not know precisely how to formulate holography in a spacetime with positive cosmological constant like the one we inhabit. We do not know whether dark energy is truly a constant vacuum energy or something more dynamic that could change in the far future. And we do not know whether Hawking radiation is the final word on black hole evaporation, or whether new physics appears near the Planck scale. One of the sharpest unresolved issues is the black hole information problem. If a black hole forms from matter in a pure quantum state, and then evaporates by emitting Hawking radiation that looks purely thermal, it seems that the final state is mixed. That would mean information has been lost. But in standard quantum mechanics, the evolution of a closed system is unitary. It preserves information. So something does not fit. Either our semi-classical calculation of Hawking radiation is missing subtle correlations that preserve information, or the classical notion of a horizon is modified in quantum gravity, or quantum mechanics itself needs to be changed. Most physicists believe that information is not lost and that a full theory of quantum gravity will resolve the paradox in a unitary way, but we do not have a consensus on the exact mechanism. This information problem is directly tied to entropy. If the entropy of a black hole counts the number of microstates, then the process of formation and evaporation should be describable as a unitary evolution between different microstates, even if the coarse-grained description looks thermal. In holographic setups like AD-SCFT, we can see this explicitly. The boundary theory is manifestly unitary, so black hole evaporation in the bulk must be unitary as well. But translating that insight to our universe with dark energy and to realistic black holes in an expanding spacetime is still an open challenge. There is also an interesting connection between black hole entropy and the large-scale arrow of time. The early universe, just after the Big Bang, was hot and dense. The entropy in radiation was high, but the gravitational field was in a very low entropy configuration. Matter was almost uniformly distributed. Over time, small fluctuations grew under gravity into galaxies, clusters, and eventually black holes. As black holes formed and grew, the entropy of the gravitational sector increased dramatically. So black hole entropy is part of how the universe moves from a low entropy gravitational state to a high entropy one. Dark matter plays a key role in seeding this structure. Dark energy changes how fast structures can grow and when that growth effectively stops. So the interplay of dark matter, dark energy, and gravity shapes the entropy history of the cosmos. Another subtle question is how to define entropy in an expanding universe with horizons. In flat space, I can imagine an isolated box and talk about its entropy. In cosmology, the universe is expanding, and there are horizons that limit what any observer can see. Entropy becomes observer-dependent. The entropy inside a comoving volume changes as matter flows in and out, as black holes form and evaporate, and as the cosmic horizon evolves. When I talk about the entropy of the universe, I usually mean the entropy within our observable region, but that is not a fixed box. The observable region grows with time, and in a dark energy-dominated era, it approaches a finite size determined by the cosmological constant. So even the notion of total entropy has to be handled carefully. Let me also return briefly to the microscopic side. The fact that black hole entropy scales with area suggests that the number of degrees of freedom per unit area is about 1 per Planck area. That is an enormous density of information. If I imagine tiling the horizon with Planck-sized pixels, each pixel would carry about 1 bit of information. This is a crude picture, but it gives a sense of scale. It also suggests that spacetime at the Planck scale is not smooth. It likely has a discrete or highly quantum structure. We do not know the exact nature of that structure. Different quantum gravity approaches propose different pictures. But black hole entropy strongly hints that the smooth geometry of general relativity is an emergent, coarse-grained description, like fluid dynamics is an emergent description of underlying molecules. This emergent viewpoint might extend beyond black holes. Some researchers have suggested that gravity itself could be a kind of entropic or thermodynamic effect, arising from the statistical behavior of microscopic degrees of freedom of spacetime. In some models, the Einstein equations of general relativity can be derived from assumptions about entropy and the Clausius relation, which relates heat flow to entropy change. While these ideas are intriguing, they are not yet a complete or universally accepted theory. But they show how black hole entropy pushes us to rethink gravity, not just as a geometric theory, but as a thermodynamic one. When I connect all these threads, I see black hole entropy as a bridge. It connects the small scale of quantum fields and Planck units to the large scale of cosmic expansion and dark energy. It connects the dynamics of gravitational collapse in dark matter halos to the long-term fate of information in the universe. It connects the local physics near an event horizon to the global structure of space-time and its horizons. And it does all this through a very concrete quantity, S equals A 4 LP squared. Yet for all this progress, a key question remains unresolved, and I will end with it. We have a beautiful formula for black hole entropy. We have semi-classical derivations and partial microscopic explanations. We know that black holes dominate the entropy of the current universe and likely shape its thermodynamic future. But we still do not have a complete, experimentally confirmed theory that tells us exactly what the microstates are that this entropy is counting in our real, expanding, dark energy-dominated universe. In other words, what, in precise physical terms, are the underlying quantum degrees of freedom of spacetime whose counting gives the Bekenstein-Hawking entropy for the black holes we actually observe?